In this video, we're going to be looking at the important ideas around spatial frequency, which are so important in understanding magnetic resonance imaging. To do that, we're going to use these slides here on the screen, and we're going to start at the beginning with a magnetic field and a magnetization vector for our atomic nuclei in thermal equilibrium. Of course, what we need to do to start the magnetic resonance experiment is to tip that magnetization vector away from equilibrium, which we do with the oscillating transverse magnetic field. Once we've done that, of course, the nuclear magnetization will precess around in the transverse plane. And the precession frequency depends upon the field strength, using this Larmor equation that we saw earlier. Now, as these spins precess around, they have different orientations in the transverse plane. And in physics, the way we describe that is through the idea of phase. Phase tells us the angle that the magnetization vector has in that precession in the transverse plane. And the mathematical description of phase is through something called a phase factor, which is a complex exponential function, which in the argument has the product of the Larmor frequency gamma b0 and the time. And of course that product there between frequency and time makes an angle in radians. So the phase angle is what appears in the argument of this exponential function. Now we want to look at what happens in an imaging experiment where we have a magnetic field that varies with position. How do we make that happen? We use the gradient coil idea. And here's a very simple representation of what a gradient coil might look like. You see we have two solenoids there, and they're wound so that the currents operate in different directions, in different senses. So in the top coil, it produces an additional field that's pointing up, and in the bottom coil, a field that's pointing down. And right in the middle, the additional field will be zero. And what a system of coils like that will do is to produce a variation in magnetic field along the vertical axis where there is a linear dependence upon position. So how do we write the Larmor equation describing the frequency of precession of the spins in this particular case? As before, we have the term which comes about from the large static magnetic field gamma b0. But because of the additional gradient coil field, we have an additional term. And that term adds another element to the frequency here, where the frequency depends upon position along the z-axis here. And the constant of proportionality with position is the gradient itself. It tells us the rate at which the magnetic field varies along the z-axis. The gradient, therefore, will be expressed in units of Teslas per metre, in the sense that we express a magnetic field strength in Teslas. So the product here of gamma, G and Z will make an angular frequency in radians per second. What is that going to do to the atomic nuclei that are in different positions along the axis of this gradient coil? Here on the right, I'm showing a set of magnetization vectors which all start together with the same phase, but they're distributed along that axis at different positions. So what that will mean is that each of those magnetization vectors is going to experience an additional field from the gradient coil which will vary according to where they are. And so their subsequent precession will occur at different rates. And we can see that by the way that these magnetization vectors get out of step with each other. But notice they get out of step in a very special way, because the phase angle they acquire depends upon their position. And that position varies linearly along the vertical axis. And if you have a phase that is built up that's linear with position, what happens is that you wind a helix of phase in the spin system. So let's go back to how an MRI experiment might work. And as always, we represent that by a time sequence where we apply to the spins the radio frequency pulses or the oscillating magnetic fields required to produce the resonant effect, and we acquire the signal subsequently. And this is, of course, the most simple experiment, the free induction decay experiment. We'll start off here without any magnetic field gradients present and just remind ourselves what happens. After the 90-degree pulse of the oscillating transverse magnetic field, the magnetization vectors of all our atomic nuclei are tipped into the transverse plane. And here, as before, I've represented them as different sets of atomic nuclei at different positions along the vertical axis. And all those magnetisation vectors start off together in phase. Subsequently, with time, of course, they'll precess all at the same Lyell frequency, and we'll have the free induction decay, which will have a reducing amplitude with time because of relaxation. Now look at this experiment when a gradient field is present. Suppose we have a magnetic field gradient that we switch on at some period of time after the 90-degree pulse, and maybe at some later time we switch it off. Let's look at what that will do to the nuclear magnetisation vectors. They all start off together in phase, all in step with each other, and as we saw before, because of the presence of the magnetic field gradient, they start to acquire different phases depending upon where they are. And those different phases cause a helical variation in phase along the vertical axis because the magnetic field gradient is a field that's proportional to position. And as time goes on, that helix winds tighter and tighter. The pitch of the helix gets shorter and shorter. Just to make more clear that helix shape, I put a little red dot here at the ends of each of the vectors. You can see the helix very clearly, and you can see that there's a characteristic wavelength of the helix, and that wavelength gets shorter and shorter with time as the effect of the magnetic field gradient winds up more and more phase difference in the spin system. How do we describe that changing wavelength? To do that, we introduce the idea of the wave vector k, and this is the spatial frequency idea that I spoke about earlier. When we think about frequency in relationship to time, frequency is related to the inverse of the period. In fact, we write angular frequency as 2 pi upon the period. In the same way, we write the spatial frequency as 2 pi upon the wavelength. And so k is in units of inverse meters. So as lambda gets smaller and smaller with increasing time, that means that k must get larger and larger with increasing time. And the relationship between the wave vector k and time is this equation here. K is equal to the magnetogyric ratio multiplied by the gradient multiplied by time. So what would happen if we were to obtain a signal at some particular point in time here when we've wound up these different phases in the spins? The signal would come about from the sum of the contributions of all the atomic nuclei. So our signal would have to involve a summation, which is represented by this integral sign here. And what would we be summing up? We'd be summing up the contribution of each individual spin at different positions. Of course, there may not be equal numbers of atomic nuclei at different positions, and indeed that would be the reason we would carry out an imaging experiment to try to find out the distribution of atomic nuclei in space. So we need something that tells us about how many nuclei there are at different positions along this one-dimensional axis. And that's this function here. This is the spin density written in terms of the Greek letter rho, and it's a function of z, the position along the axis. And for each of those sets of spins at different positions, they've got their own special phase factors. The phase factors that are related to where they are on that particular helix. And here I'm using the k-space notation to write the phase factor. So the phase factor is a product of the wave vector k and the position z. So what we have here is an integral which sums up all the contributions of the nuclei, allows for how many there are at every different position, and allows for their different phase factors. Of course, the signal we acquire is not the thing we're really interested in. What we're really interested in is imaging is this spin density function. That's what we saw when we looked at the one-dimensional imaging experiment with the 2 tubes of water. The signal we acquired in time also corresponds to a signal in k-space because k is proportional to time. And when we Fourier transform that to get the frequency domain, we obtain the image. So where is this Fourier idea present in the idea of k-space and real space? That expression is in fact a Fourier transformation. The signal we require in the spatial frequency domain, we need to convert into the density in real space. And the relationship between S of k and rho of z, of course, is simply a Fourier transformation. So that signal we acquire is Fourier transformed to obtain the spin density. And that's the fundamental basis of magnetic resonance imaging. Here we've seen it in one dimension. What we need to do now is to expand those ideas and look at it in 2 or more dimensions.